High above our heads, there's this invisible ocean. It's a massive region of charged particles, totally forged by the sun. And it's kind of ironic, because it's the very thing that first connected our world, but now it messes with our most advanced technology. Today, we're pulling back the curtain on the ionosphere, Earth's unseen and seriously powerful influencer.
To really get a handle on the ionosphere, we actually have to go back in time. We've got to solve a mystery that completely stumped some of the sharpest minds of the early 20th century, and it all kicks off with one simple question.
Think about it for a second. Radio waves, just like a beam of light, travel in a straight line. They can't just bend around the curve of the Earth. So how in the world, back in 1901, did a signal manage to hop all the way across the Atlantic Ocean? I mean, on paper, it looked completely impossible.
But Guglielmo Marconi, well, he was convinced he could do it. And so on that chilly December day, his team in Canada was out there holding this massive antenna up with a kite, just listening. And then they heard it. 3 faint little dots. Beep, beep, beep. The letter S. That little signal had traveled over 2,000 miles, a feat that just flew in the face of everything they knew about physics at the time.
Now, the solution to this puzzle wasn't some big eureka moment. No, it was more like a slow drip of clues that took almost 100 years to piece together. The first hint came way back in 1839. Then, right after Marconi's big success in 1902, 2 scientists, Heaviside and Kennelly, both came up with the same idea. There must be some kind of reflective layer up there bouncing the signal. But it took until 1926 for it to get its official name, the ionosphere, and another 20 years before it was so solidly proven that it earned a Nobel Prize.
So this number, 1.5 megahertz, it seems pretty random, right? But it's at the heart of a totally accidental discovery. See, back in 1912, amateur radio buffs were told they could only use frequencies above this number. The professionals thought those frequencies were useless junk. But what happened? By messing around on these so-called junk frequencies, those very amateurs discovered in 1923 that their signals were bouncing off the sky, unlocking the secret to long-distance radio. Kind of funny, huh?
Okay, so Marconi's mystery is solved. There's a giant mirror in the sky. But what is this mirror, and how in the world did it get there? Well, the answer is about 93 million miles away, with our sun.
The ionosphere isn't really a single layer you can point to, like the ozone layer. It's this huge, sprawling, dynamic part of our upper atmosphere. It gets started about 30 miles up and stretches all the way out to over 600 miles into space. And this entire region, this whole thing, exists because of one process, ionization, and it's all driven by the sun's incredible power.
So how's this cosmic mirror get made? It's basically a 3-step dance. First, the sun blots out all this high-energy radiation. We're talking powerful UV and X-rays. Second, that energy comes screaming into our upper atmosphere and just smashes into the gas atoms up there. And third, that collision is so violent it literally knocks electrons right off the atoms. What you're left with is a sea of positively charged ions and all these free-floating electrons. That electrified gas is called a plasma, and that is the ionosphere.
But here's the thing, this plasma isn't just one big uniform blob. As you go higher up through the atmosphere, it actually splits into different regions, or layers. So let's take a quick journey upward, because each layer has its own personality and its own way of messing with radio waves.
Okay, so the lowest layer we hit is the D layer. It's pretty dense, and it actually absorbs AM radio waves. This is the reason you can hear those distant AM stations so much better at night. The D layer basically vanishes when the sun goes down. A little higher up, you've got the E layer, which bounces some of the lower frequencies. But the real star of the show, the long-distance champion, is the F layer. It's the highest, the most charged up, and it's the one that does the heavy lifting, bouncing high-frequency signals clear across the planet.
And here's where it gets its name. It's just a perfect example of the scientific process. After decades of people talking about a conducting layer, this guy, Robert Watson Watt, writes in a letter in 1926 and basically says, hey, the main thing about this place is all the ions. Let's just call it the ionosphere. Simple, elegant, and it's stuck.
Now, it's so easy to picture the ionosphere as this calm, predictable, glassy mirror up there. But the reality? It is so much more chaotic than that. It's a wild, turbulent, and constantly changing environment. Just take something called the winter anomaly. Your logic would tell you, hey, more direct sunlight in the summer means the ionosphere should be stronger, right? Nope. It's the opposite.
In the northern hemisphere, that all-important F layer is actually more ionized in the dead of winter. It turns out that seasonal changes in the atmosphere's chemistry mean the ions stick around longer, making winter, weirdly enough, better for long-distance radio. It's completely counterintuitive.
And the weirdness does not stop there. You've got the equatorial anomaly, which is like a plasma fountain that creates these two big bands of ionization on either side of the magnetic equator. And then you get sudden violent events. A solar flare can erupt and bam, instantly cause a radio blackout. Or a stream of solar protons can get funneled down to the poles and just absorb all radio signals for days on end. It is anything but calm up there.
So, all this turbulence and chaos hundreds of kilometers above our heads, why should we care? Well, because that same chaotic layer that gave us global communication is now a massive headache for the technology we depend on every single second of every day.
Seriously, every single time you pull up directions on your phone, signals from a whole constellation of GPS satellites have to punch their way through the ionosphere to get to you. And as they pass through that sea of plasma, they get bent, they get slowed down. If we didn't account for that, your GPS would be useless.
So, how do we fix it? With some incredibly complicated math. That's how. The American GPS system uses a model called Klobuchar, which was actually developed back in the 70s. It's pretty good. It gets rid of about half the error. But Europe's newer Galileo system, well, it uses a more advanced model called NEQUIC that can cancel out up to 70% of that delay. And that right there is the key takeaway. Without constantly modeling and predicting what this wild, invisible ocean above us is doing, that little blue dot on your map could easily be off by 50 feet, maybe more. Our entire global navigation system is completely dependent on us understanding the ionosphere.
So we're left with this incredible paradox. The very same layer of our atmosphere that first let us talk to each other across oceans is now one of the biggest sources of error for our modern satellite tech. It really makes you wonder, as we become more and more reliant on space, what's the next great leap going to be? What will it take to finally predict and maybe even master this turbulent frontier right above our heads?